Okay, so this is the recording of chapter 9, Shear. So now we're going to design. We have used some of the formulas in chapter 5, but this is now when we're actually going to apply for design. There's a lot of discussion here about the history, things about formulas for shear. Please don't worry about it. Okay, here is just a typical shear failure. It normally starts some point here, neutral axis. I think it propagates around the tension side, and it usually kind of follows the line of the rebars and kind of separates from it, right? And we call it like a debonding. Or it can go up, right, and then cause spalling because it's a compression failure, right? So that can be, yeah. So you remove that section, and this is kind of what you get, right, in there. So that's kind of your failures. That's that you want to remember from those figures. So that's that kind of 45, kind of a 45-degree angle failure, right? I mean, we approximate this as a 45-degree angle, okay? In there. So that's what you want to remember from this. Don't do more than that. About these parameters, again, don't worry about the history, when it happened, what year, or who did what. No, we're going to. I'm going to show you here pretty quick what we have, and I think this is the formula that we want to look at. And notice that way back, okay, this is a long time ago, we knew that the shear depends on your concrete strength, right? Depends on the amount of longitudinal steel that you have, depends on this ratio, which really is A over D, and that's called a shear span to depth ratio. And at the time we put a limit like this. That was like 14, before 14 now, right? Notice then that the shear, right, the shear strength will increase, right, as you increase your longitudinal reinforcement, and of course will increase as you increase F prime C. Now BD here is multiplying, and so it will increase with B and it will increase with D in this equation, right? But it will decrease with the A over D ratio, right? So as your A over D decreases, your V increases. As your rho increases, your V increases. So there is direct proportionality between V and amount of steel, but there is an indirect proportionality between your shear and your shear span to depth ratio. Okay? And so that's what we knew there. For a long time ago, people were saying that there is also failure due to size and that we are not accounting for the right amount of steel. And so now the code developed the new formula, right? The new formula that we have in the code. The problem with that new formula, which is in your chapter 5, and I think I copied here too, and let me jump to that for a second, and then I'll come back, because I know I copied here. Okay, right here. So the new formula, which is this one, right? We don't have that one that I just showed you a minute ago. That's been removed from the code in 2019, and so now we have these two. But this one is the new one. Okay, this one is kind of the old one. Is being modified a little bit, but it's similar. But this one is the new one. The problem with this one is you got a D here, and yes, you say, okay, it's increasing with D because I'm multiplying times D, but when you find rho W, you are dividing by D, right? And so now you got a non-linearity between the D values. Okay? So it's harder to predict that behavior now because it's a combination of that, all right? And so that's important to remember that because of that effect. Okay? This non-linearity here is more difficult to predict. Okay? But again, we still got the same thing, okay? The shear of the concrete shear strength depends on the amount of steel that you got, longitudinal steel, right? And it will increase as you increase that one. It will increase as you increase your strength, right? It will increase with BW. It's supposed to be increasing also with the D value, right? And so we got the same thing. The only thing that is not here yet, and some people want to put it in there, is the shear span ratio, okay? So we lose one, some people win this one by putting the raw W, but they lost the other one, so they didn't put the shear span to depth ratio. Okay? But the shear span to depth ratio is an important concept, and so we are going to look at a bit about that one. So let's go back here again. So I saw, okay, so we came back here. Don't worry about this development of this equation. No, nothing like this. All I was looking at, this is the old equation from ACI. This is ACI 318.14. Okay, 14 had this equation. And this is what I want you to look at, because this is now what happens. This one is that equation, the ACI 318.14, which you see here, it ends at 3.5. Okay? 3.5. And so that's that equation. This one right here, that's the 2. Okay? 2 squared of f prime c b d. So that's that one. That's the simplified equation in 14, which is also the one that we have in 19. This is the first equation. Your second equation in 19 varies with rho w. So depending on the value of rho w, you will get different values. But now they have a maximum of 5 rather than 3.5. So the new equation, notice that it covers all the way down to here, right? Covers all those cases, and it covers pretty much all these cases. So you have all these cases covered, right? The new equation will give you exactly the 2 value right here when the rho w is 1.56%. You will get the same. Okay? So that's what we have now. So either you use the equation 2, because that's what the code says, you can use either equation, this one, or you use the equation with the rho w, and you will have different values depending on where you are. Okay, that's all you need to know about that. Don't worry about this. Here is another view of what is the shear span to depth ratio. So this is the shear span. Okay? Notice that it's simply your moment at this location divided by your reaction here, which is equal to the load, so that gives you A, right? So shear span divided by D, right? And of course, depending on the length of the beam, you get different values. Okay? But that's your shear span to depth ratio. Now, in most cases, we do not have really a point load, so you don't have an A value. But what you do have is a moment at that point, at that location, and it's shear. So then what we define as shear span ratio is your moment divided by your V. Okay? And so that gives you a shear span ratio for uniform loads. Okay? Moment divided by V. That's your shear span ratio. Okay? Okay, so make sure that if you have a point load, it's easy to find that value. But if you don't have a point load, then it's moment divided by shear. All right, so that's about shear span ratio. That's a good thing to know. Okay, you don't want to worry about this. Nothing here, nothing to worry about here. Now we start here. What do we have here? What is this? You're going to go back to mechanics of solids, so let me hypnotize you here, okay? Pay attention, okay? I'm going back to mechanics of solids, okay? So yeah, okay. Now you're back in mechanics of solids, and you see this beam, right? And you learn about flexural stresses and shear stresses. Now you're remembering all that. And what happens on the neutral axis? Your bending stresses are 0. Yes, see, you're remembering. Okay, so 0 shear is bending stresses on the neutral axis. But your shear stresses are maximum, right? And so maximum shear stresses on the neutral axis, 0 stresses for flexural at the neutral axis. So the neutral axis, you have this thing, remember, from Morse circle, right? The little element, right? The square. So all you have is shears. Okay. And then you apply Morse circle. Oh gosh, Morse circle, right? You apply Morse circle, now you get your principal stresses, and there is a tension stress that is a 45 degrees from this plane. So right in this plane. So notice that these two forces right here and that one kind of point out and then go that way. So they're going that way. So you can stretching. You pick you pick the two corners, right, and you pull it. That's what you get, right? You get this. So that is your playing out of maximum stresses, and you got tensile stresses. So in concrete, when you see a crack, it's not the shear, it's not that, it's not something else. It's always a tension. Okay, so the tension is perpendicular to the crack. Okay. All right. So the true shear cracks are called the web shear cracks. Yeah? They develop right at the webs, and these are more like this kind right at the webs, right? And so they originate at the web, so that's where you start. But then they move down and they go here, or they go and crash right in the top. But they start right at the webs. So they start the webs. They have nothing to do with flexure shear cracks. They propagate toward the tension side, so they will go towards the reinforcement. They tend to happen in T-beams or I-beams, or beams. Here is important. See, that's why I talk about the shear span ratio, right? Or beams with a shear span to effective depth ratios less than or equal to 2.5. So the ratio of the moment over V and then divided by D is less than or equal to 2.5, then you may have this kind of shear cracks. So that means is the case where the moment, right? The moment is small, but the shear at this location is large. So we got that. Okay? And usually you need a force that is 3.5 times the square root of F prime C BD to initiate the crack. Okay. Now in other cases where you have large moment but low shear, what you develop is the flexure shear cracks. Okay? They're called flexure shear because they start as a flexure crack, vertical, because your tensile stresses are horizontal, so your crack has to be vertical. And then as you move up, these cracks start turning to get to the 45 degrees. Okay, so that's what they call flexure shear cracks, also diagonal tension cracks. These are the most common cracks you're going to see. They develop from the tip of the flexure crack, right? And again, it's large moment, right? In there. Need to have a V greater than 1.9, right, in order to initiate the crack. All right, so that's all you want to know there. This one right here, we don't have to do anything, nothing. Don't worry about this. Don't worry about any of that. Okay. These are other things that we need to understand. What are the components that make your concrete shear strength? There is the actual concrete in compression, the aggregate interlock, because the aggregates are not rounded, right? I mean, they have points, and so they kind of stuck in there, right? And so that's the aggregate interlock. The stirrups is the extra, right? And then your dowel action, right? All that contributes to that shear strength. And in general, I mean, this is what it was. I mean, the aggregate interlock was pretty high, and then your concrete was the rest, and your tower was a little bit. So that's why we tend to ignore that sometimes. This has changing because with the higher strength concretes, and now before the crack will go around the aggregate because the aggregate was stronger than the concrete, right? But now that the concrete is very high, you can crack the aggregate and you can go through. So then this is being reduced, as you increase your concrete strength. Okay, so that's all you want to know there. No more. Forget about this. You've never seen it. And this concept right here is useful in the sense that you can look always as a beam that looks like a truss. A truss made up of longitudinal steel. The stirrups are acting as the vertical members. Concrete acting as the compression member. And diagonals being compression struts. Okay? So the concrete acts as diagonals. Okay? So that's kind of a model to kind of come out with your shear theory, shear design. Okay? And this is what we use to develop our formulas. Remember, we did that, made the cut at 45 degrees, and we develop our formula. So that's what you have. Okay? But that's all you want to know. There is a model that looks like this, and then later when you take advanced concrete, you may learn more about how to use this to come up with another type of design. But for now, that's all. So what is the design procedure? Same as before, we need to satisfy that your design strength greater than your VU, right? And of course, your V sub n had two components, the concrete and the stirrups, right? And we work with that. The equations were developed already in chapter 5, right? And of course, the right hand side is your shear coming from your applied loads, right? And so how we're going to find this, here is some guidance. You're normally going to find your reactions, right? But the shear that you're going to design is not the actual reaction, is the value at a distance d from the face of the support, as long as your reaction is a vertical reaction. Okay? In the case of a column with a beam, the same thing. Reaction is vertical, so you take at the distance d to design the beams. Here, a joist or a beam with another beam, right? And again, reaction is vertical, so you take your shear for design purposes at a distance d. Okay? So these are the most common cases that we're going to use. And then at the bottom, we have the exceptions. Okay? If you create a tension force, then you have to take the shear at the face of the member. If you're going to design the connection, you take the values at the face. If you have a point load between the face and the distance d, you have to take your shear at the face. If you load below the neutral axis, you have to take your value at the face. Even though you have these compression forces, right? You cannot develop the arch, right? So what this is nice is because you have a load on the top and this one right here, and you are developing a nice kind of arch, okay, effect. But in this one you can't do that. So that's why. So what are these cases? The cases are here. Okay? If you are between, your VU is between V sub C and this number here, then you all have to do is check spacings. And that's all you have to do. There are 4 values you need to check. These 2 are based on the minimum requirements. Okay? Excuse me. And you always have to satisfy this. Okay? Now, the exceptions to do this is for slabs, and for joists, and for footings. Okay? For footings, everything starts above this number, the phi V sub C. So that gives you then the spacing along the length of the beam. Then the 318, the 19, the new code, also introduced the maximum spacing across the width, which is this one. This one will tell you how many legs you need in the section. Okay? So that's the first case. The second case is when you exceeded your concrete strength, right? And then you need to find your stirrups. And in that case, you have a case A, where you are below the 4 square root of f prime c BWD. Remember, we checked this in the shear, right? And in that case, you are below that, your maximum spacing is, you need to find the value, and you also have a maximum, which is d over 2 over 24. So if your S here is less than the maximum, you will use this one. If your S here is higher than the maximum, you will use the maximum. Okay. Across the width of the section, you are limited to D. Okay. This one is the case where you are between the 4 and the 8. Remember, we did that to check your capacity. So between the 4 and the 8, you are between the 4 and the 8, everything goes to halves. So now it's half of what you got here. So D over 4, 12, and this becomes D over 2. You still have to find your S. So again, if this value is less than the maximum, you use this one. If this value is greater than the maximum, you use the maximum. And this is now across. Okay. And this becomes critical now because let's say you have a beam that is 20 inches, right? Your D would be about 17 and a half. D over 2 now is 8.5, right? And if your beam is 16 inches, you cannot put 2 legs. Now you need to have 3 legs in order to satisfy 8.5 inches, okay? So this is the new requirement in 3.18.19 that has added this condition here. Now you exceed the 8, then you are in this case, that means you need to change the size of your beam, okay? So it's not working. Okay? So what you're happening here is you're creating a failure, they call it here in the compression struts, right? That are working between the hangers, which are the stirrups. So to understand that, see, this is why I talk about the truss, because a lot of the people, when they talk about shear, they talk about these things, okay? And you read it, you will not understand it, what they're talking about. And what they're talking about is simply the struts, right? The diagonals, and the hangers, which are the stirrups. So the struts between the hangers, you can cause a failure due to the compression here. You had too much of that shear. Shear pretty high, you can cause that problem. Okay? That's what they're talking about. All right, so now we know all the cases, right? And these cases has been put very nicely in your design aids. So let me go here to design aids. So design aids. Right. So in the design aids, you have this table, right? Now the only problem with this table is that it uses 318.14, and so this one, right, is no longer true. Okay? This right here has now been replaced, right? It has now been replaced by this value, right? So, but if you use, right? If you use the first equation for shear, right? You use the first equation for shear, which is this one right here, right? There's the first equation for shear. This is 0, right? Notice that you divide by 2, you get exactly that value, lambda square root of f prime c BWD, right? So that means then this is valid as long as you use the first equation for shear. So you're using the first equation for shear, this is still valid. Okay? You use the second equation, then this may not be valid. Okay? And here are your four. So in this column, the first column, right? On this column here, you have your 4 cases, right? So here's the case 1, the case 2, and this one is minimum requirements. Okay? And then here are the maximums. Right? And then when you exceed VU, right, you have to find your S, but you have again two maxims, depending if you are below the 4, which is this case, or you are greater than the 4, which is this case. Okay? And so those are the cases. So right there in one table. Okay? So that table is nothing else but all these cases that I'm describing here for you. Okay? So all these cases are in that table. Okay, so then what is this? This is simply some of the notation you're going to use. I'm going to call the VU at this location, the VU at the face. Then the value at the distance D is going to be VU at D. Okay. Normally we're going to design for the VU at D. Now for the code, there is no VU at D or VU at the face. There is a VU. And VU is every line here is a VU. Right? Because this is your VU shear diagram. Right? This is the half of the shear diagram for a uniform load. Okay? This portion right here is what the concrete can do, and the difference has to be taken by the stirrup. Okay? Now, if the concrete can carry this, then you will say, well, I don't need to do anything after this point. But the code says, no. You have to go to this point. Okay? And you have to put the stirrups there. Okay? So up to this point, you have to design the stirrups. Beyond that, you don't need to design the stirrups. Now, how do you specify your stirrups? You will say 1 at 2 inches or 1 at 3 inches. And then you will say maybe 10 or 12, whatever you need, 8 at a new spacing. And you may change the spacing between this point and this point. And then because this is going down, you may change the spacing between this and that. And then you change between this and this, right? And so you may have 3 different spacings that you may specify. Okay? And we're going to see what that means later in the examples. Okay, so no more than 3 different spacings, not counting these ones. Okay? And the other thing we need to understand is what happens at the center of the beam. Right? Remember that envelope that we use with the coefficients. Right? Okay, so what is happening there? Well, for those of you that already took analysis, right, or maybe I've taken it, right, you probably heard about something called influence lines. Well, this is the influence lines for a shear at this location. Okay. And so what this tells me is that if I want the maximum shear here, I need to load only on one side of the beam. And there it is. Okay. So if I want maximum shears at these different locations, right, all these different locations, I had to load the right-hand side of the beam. So I'm going to do that, right? But one point that is the most interest here is what happens in the middle. Right? In the middle, okay, I'm going to load only half. But which load can be changed to half of the span? Yes, only the live load, right? Your dead load is always present, right? But your live load could be only half of that portion. So then that depends only on the live load. So this is a factor live load. I find my reaction, you can do that by equilibrium, that happens to be this number, and therefore that's my reaction, then my shear is constant here, it has that number, and so this is now my shear at this point. Okay? So now I know my shear there. So I have that number right here. Okay? So notice this is the reason why this line didn't go to 0 anymore, right? They didn't match. The lines did not match anymore, right? Excuse me. Now, but that's because we did this point. But in reality, you are doing, remember, you're doing a point here, a point here, point here, point here, point here, middle, right? You're doing all these points. So what it means, you're getting different values, and these are what these dots are. So that's the true envelope. But we're going to be conservative. We're going to take the maximum here, the maximum in the middle, and we join it by the straight line, and we're going to say that's my approximate envelope. Okay. This is the diagram that we used to have. This is the one that you learned that it goes to 0, right, for a uniform load. Right? This is the diagram that you learn in mechanics of solids. Right? It goes right through 0, but that's because you didn't find maximums. Right? But now we know better. There is a value here in the middle. It's not 0. Just to give you an example of what that value is, here is a typical slab of 6 inches with 30 PSF additional dead load, a live load of 100, the beam 18 by 24, tributary width is 12. So we find our loads, right? Weight of the beam, we added all that, weight of the slab, weight of the beam, the extra 30 PSF, the 100 here, all multiplied by the tributary width, and we got our two loads. This is the factor dead load, this is the factor live load. So approximately 4. So we load, our value is 56,000. And the distance D, my value is 48,800. So that's my shear that I'm going to design for in general. Now if I do the partial live load, I will get something in the middle, and that value will be this value. So this value is only about 14% of this one. So it's not a big value. Right? So usually you use minimum reinforcement, you can cover that number. All right? And so that's why we normally do that, because in this case, for example, the beam already has a strength of 31, almost 32, right? Compared to 6, we are good. Even half of this is already bigger than this, right? So normally we are good, okay? Now you don't want to use this equation and you know your raw value, you can use the other equation, right? Which can give you a lower value sometimes. So in most cases, then your shear in the middle, due to half of the live load, can be normally carried just by the concrete. So we don't need to do much. Effective taper you don't have to do, so you forget about this. And shear reinforcement in joists, all you need to know here, I think, is the types, right? So if you have regular standard joists, remember you can increase your shear by 10%, and you don't need to put stirrups if you are below Phoebe sub C, it's 10. But if you're not a standard joist, your value is this one. Okay, have that. The stirrups can have the shape with this one. This one is a special one. That's very typical. I use it a lot. It looks like a bar like this, but really is more like this. So this is along the length of the beam, and this is just looking at the cross section. Okay, you only see one bar, which is that, but really it looks like this. And so that's another stirrup. You can do this one, but it's hard to place. And what people do is, you don't have enough space, they put it at an angle like this, and then you make it fit. But those are typical shear reinforcement. Okay, so now we get into design. We need to satisfy minimum in order to use these equations. Otherwise, we cannot use this equation. We have to use the third equation, right? And these two equations will be equal, as I said, when the percentage here for the raw W is 1.56%. Okay? At that moment, both are equal. You put less, this one gives you less. You put more, this one gives you more. Now, the examples that we're going to do are going to be based on this equation. Okay? These examples you are not going to see. That will be next semester. So hopefully none of you will be staying for that. And so we were going to use this one. Okay. So we start here, one beam, right? Simply supported beam, clear span, 22, loads, so given there, all service loads, strength, yeah, 4,000, 60,000, D value, 12, 20. Right? So we find the beam weight, we do our load combinations, and we have our load. In reality, you've been doing your design already, right? You already know your load. You already know your D. That's what I'm giving that to you here. Okay? Because that was part of your design. No? So you find your shear. So this is my shear at the reaction here. Now, in this case, the reaction is a shear because it is a simply support, right? So careful. What we need is the shear at the distance D. So what I do is then I'm going to take my reaction and I'm going to subtract the load multiplied by the distance D. So 36.3 minus my load times the distance D, change it to feet. And this is the shear I'm going to design for. You can round it to 32. Okay, that would be fine. Then you find your V sub C. There it is. Multiply by phi factor, always 0.75, you get that one. Now, if you are using this equation, then this limit happens to be exactly half of that number. So 19.4, 9.7. Okay? That's the beauty of using that one. You use the second equation, that will not happen. All right, so what do we have so far? Reaction, 36. Shear at the distance D, 3163. Okay. Phi B sub C, that's how much the concrete can carry, 19.4. This limit, 9.7. The code says you have to put a stirrup between this point and this point. So I need to find what that number is, right? I color-coded so you know how to find it. So right here. Right? So how are we going to do that? You can look at doing a triangle here, big triangle, with small triangle. Right? So we have 36.3 proportional to 132 as 9.7 proportional to Z. Right? So we have that, solve for that, and then my actual length will be 132 minus the Z value. So that gives me that. So that's using proportion. The other way to do it is by using your shear equations from mechanics of solids, right? Or using your beam formulas. So what is my shear equation? What is my shear at the distance X? Right? Will be here my reaction minus my load times X. And what do I want? I want to know the value of X when the shear is 9.7. Okay? That's what I want. What is the value of X when my shear equals 9.7? So what is this distance so that this value is 9.7, right? So we make then the shear 9.7, we're solving for X, and that X is the length of stirrups and is 97. You can do that. Okay? So either way, whatever you like, you can do that. Because my my VU, right, which is BU here 3163, is bigger than my phi B sub C, right? Then I need to use the second column on that table. Remember, so we're in case 2, right? And so we are going to find our maximum spacings based on that. But we need to find V sub S. So first we're going to find phi V sub S, which is VU minus phi B sub C. And because this is phi v sub s, in order to make it a v sub s, we divide by phi, and that will be 0.75, and then we have v sub s. Then we compare this number against the 4 and the 8, right? And we decide where we are. In this case, we are below, and therefore my maximum is limited to these values, which gives me 8.5. Okay? So that means that within the distance d and all that, I can use 8.5. Now, as I go down eventually I will get to check minimums, right? And actually, you should always check minimums. You should always check, make sure that you satisfy these minimums. But notice that here it's also controlling 8.5. So then, so far, what we have found is that from here to the v sub c, we have a maximum spacing of 8.5. From here to the 9.7, we also have a maximum spacing of 8.5. Okay? So all these are in column 2 of that table, and these are in column 1 of the table. So this is my column 1, my column 2. Okay? So that's where we are. Okay? So column 1, column 2. Excuse me, column 2, column 1. Okay? Across, right? Remember the number of legs. It requires that the spacing be 17 inches. My beam is only 12 inches, so the legs are going to be a lot less than this, so we're good. Right? Next, we're going to find the S value. Right? So now we are looking at finding these number here. Right? So we need to find the S value. Okay? And this is my S required, okay? Because it's what I need based on my shear. So I calculate my S is 13.8. It's a lot bigger than my 8. So 8 controls. And so the 8.5 now is going to be round down to 8. And then we're going to select our stirrups. Now, normally we will need to create a table because the shear is varying, right? So I need to find different spacings. But in this case, because the maximum is the same and I cannot exceed it, and this value is already bigger, right? Then the smallest I can use, the largest spacing I can use is 8 inches. I can use anything less, but I cannot exceed that 8 inches. Okay? So that means that we are going to put then 1 at 2 inches and 12 at 8 inches. And that covers 98 inches, which is bigger than my 97 that I needed to cover. Remember my length of stirrups. That's my design, okay? So now I have covered that. So the problem is what happens to this portion. Now, if in this section I do not use the minimum amount of stirrups, I have to use the third equation. Guys, that's more work. I don't want to do that. So I'm going to add a couple of stirrups here, whatever I need, to satisfy minimum spacing, which is 22. Out of these two, right? This is the minimum. So out of these two, 22 controls, right? Always the lowest. So I need to put some stirrups to make sure they will satisfy that. Well, how much distance do I have? I already covered 98. To get all the way to the middle, which is 132, so 132 minus 98, I need to cover another 34. Well, I can do that by adding 2 more stirrups, and those will be at 17 inches, right? And 17 inches is less than 22. That satisfies AB minimum, so my equations are good. I don't have to change equations. Okay? And that will be my design. Okay? So that's the basic design. That's the simplest you can have, the easiest design in shear. Okay? Anything else gets more complicated. Okay? So we're going to stop here so you can have time to digest this one, and then I'll do more examples.